Introduction to Memory Technology and Products, and it will be covered by Kalyan and Venkat from Micron Technology. This particular tutorial will cover DRAM and NAND memory products, playing a key role in transforming the data processed by the various diverse compute, communication, and AI/ML systems into intelligence. It will provide an introduction to the NAND and DRAM semiconductor memory designs, highlighting some of their characteristics and challenges. This will be covered in two parts. Part one will be covered by Kalyan, which will be all about NAND flash memory, and part two will be covered by Venkat, which will be talking about LPDDR4 architecture. Before we start, let me introduce a little bit on Kalyan and Venkat both. So Mr. Kalyan is a director in NAND design in Micron Technology India, and he has joined Micron in July 2006 in the non-volatile memory group in San Jose, California, as an analog design engineer in NAND design team. Prior to that, he had worked as test engineering intern in Intel, Arizona. In the first 13 years of his career in Silicon Valley in various roles in NAND design group, ranging from an individual contributor to integration lead, he has authored and co-authored 20 patents till date. He moved back to India in 2019 and has taken up a challenging role as director NAND design, building the team to deliver the NAND projects. He earned his undergraduate in electronics and communication from Osmania University, followed by MS in electrical energy engineering from Arizona State. Let me also introduce the other speaker, Mr. Venkat. Mr. Venkatraghavan is a director in Micron India and leads the DRAM and emerging memory team. His 20 years of industry experience spans around DRAM, SRAM, and register file development. In the past, he has been associated with Micron USA, IBM, and Global Foundries, along with Marvell. He has over 54 US patents which are granted, and many of his patents are actively powering up several customer chips. He has mentored over a dozen team members in their patents and nurtured employees on technical leadership. Mr. Venkat holds a master's degree in electronic and computer engineering, University of Nevada, USA, and bachelor's in electronics and communication engineering from University of Madras. He is a recipient of IBM Innovation Excellence Award and recognized as Master Inventor at the Global Foundries. With this, I will hand over the session to Mr. Kalyan and Mr. Venkat for a very thoughtful tutorial that we have ahead.
Thanks for the nice introduction, Mr. Ashutosh. So my full name is Venkatraghavan, Bringivijayaraghavan, and I go by Venkat Bringi. So the topic that I'm going to present today is an overview of the DRAM functional blocks. Yeah, here is a quick agenda. So I will go through the DRAM family, the different families that we have in the DRAM memory, and then I'll go through the functional blocks. And when I go through the functional blocks, we'll talk about the priorities in DRAM and the requirements and the opportunities that presents to the engineers. And I'll take a little bit about Micron and finally end with the Q&A. So before we enter into the DRAM family, let me quickly go through the basic principle of how a DRAM memory operates. So the fundamental principle of DRAM operation is a 1T 1C cell, which is one transistor and one capacitor. This is the 1T 1C that I was saying, and we have the capacitor, and the capacitor is connected, one end is connected to the access device, and the other end of the access transistor is connected to the digital line. So the gate of the access device is connected to the word line. This is the DRAM, which is nothing but the dynamic random access memory. So the common node of the capacitor is biased at VCC02, where VCC is the supply, memory supply. So the charge that is shared, stored in the cell, which is depending upon whether it's a 1 or a 0, it can be plus or minus VCC02 across this capacitor. So for storing a 1, what we do is like we write a full VCC into this cell. So the charge across the capacitor is VCC02 times C cell. For storing a 0, it is exactly the opposite. It's negative VCC02. So when we want to access this cell, we enable the word line. And when the word line is enabled, depending upon what you have stored, whether you have stored a 0 or a 1, then the signal that is developed on this digital line is just a charge sharing between this capacitive digit line versus the storage node, which is nothing but like this formula. So essentially, what happens is the digit line is really capacitive. We try to make it like very capacitive so that we can make the memory very compact. Based on the latest technology, if the supply is 1 volt and the V cell will be like plus or minus 0.5, if the digit line is 50 femtofarads and the capacitance of the storage node or the storage cell is 10 femtofarads, then the signal development that we see based on applying this formula, it will be like plus or minus 83 millivolts. So that says like how much of a less signal development that happens, and we need to sense with a complex sense amplifier. So this is a basic principle of a DRAM. With that, let me introduce the different DRAM family that we have. Broadly, we can categorize the DRAM as like compute family, mobile family, and graphics family. Now, depending upon the applications, this is the way this has been, I have categorized is primarily based upon the applications, the power and performance profile that is needed for each one of these applications, and the features, some of the features that are unique for these families. So for example, the compute family, typically the compute family is, the memories that used in the compute family will be like in servers, data center, networking, our computers and laptops, right? That's where the DRAM that is used in these applications is what we call as a compute family. Now, the DRAM that is used here requires very high density, because whenever we go for buying a laptop or a desktop, we see like how much memory, what is the RAM capacity, right? So we really look for high density and also high form factor. Because we want really like it is used in the server applications, right? We really look for a wider channel. So the channel can be like 64-bit wide or 128-bit wide, depending upon the application again. The common memories that are used in the compute family now is like DDR4, that's the DDR4 and DDR5, those are the mainstream. And it comes from a variety of densities starting from 8 gigabit to 32 gigabit. And we can expand even up to 64 gigabit. When I say the 8 gigabit, that is the size of one individual memory component chip. And they come at different form factors. You would have heard like DIMM, the dual inline module. So it comes with SODIMM, small outline DIMM, which is primarily used in laptops, and RDIMM, which is a rebuffered DIMM that's used in servers. I'll have a picture that shows some of these form factors and package. Now, when it comes to mobile, as the name says, it's primarily used in mobile applications like your tabs, like your mobile phone, automotive and IoT applications. For these applications, the primary target is we want it to be low power because we want the battery to operate for longer time. And also, given the size of these devices, it's very highly sensitive to the form factor. So, for example, if you see our mobile phone, the silicon area there is like, we need to make the best use of the silicon area there. So then it becomes highly form factor sensitive. We call it as like LPDDR4, low power DDR4 and low power DDR5. That is the name for the mobile memory. And again, it comes from variety of densities from 8 gigabit to 32 gigabit. How the compute memories come in like DIMM and SODIMM. Here, the form factor or the package for these memories is like MCP, a multi-chip package, or package on package. And the last family, that's the graphics. The graphics primarily used in gaming applications or any accelerators, network switches, or any AI-related applications, right? These are the applications where the graphics chips or memory is used. And the typical characteristics of graphics chips is like it operates at very high speed and with very high throughput. Throughput is nothing but number of bits that comes out of the memory component.
Venkat sir, sorry interrupting you again. The slides are not moving, neither it's in presentation mode. We can still see slide 4. If you're still on slide 4, great. Otherwise, and the slides
So,
are not moving, and as well as we do not see the presentation mode.
Okay, now it's in the presentation mode.
Yep. Now we can see DRAM family slide. That's the one that you were talking about?
Yeah, I was talking about the different families here.
Thank you. Please continue.
Yeah. So graphics DDR5 and graphics DDR6, that is the typical mainstream memory, and HBM also comes under this family. And they are available in densities from 8 gigabit to 16 gigabit. So let me quickly show the package, the form factor that I was talking. So this is a DIMM module, and this DIMM module, this is the memory that is used in our laptops.
Recording stopped.
This is what is used in desktops, laptop servers. So this is the compute memory, and you can see each one of these components is glued to this DIMM module, and this is what interfaces with the rest of the system. Now, when it comes to a mobile phone,
recording in progress.
When it comes to a mobile phone, I'm showing here two packages. This is like a package on package where you have the LPDRAM along with the flash controller, all of it in one package, and that is what sits in your mobile phone. The last one I was saying, that is the GPU family. So on the GPU, as you can see here, you have the GPU processor, and you have so many of these memory components that is interacting with the graphics processor. The reason why we have so many of them interacting in this fashion is like all of this, like you need very high throughput, very wide channel, and it is like data hungry. All of it is being catered by so many of these memory components that is interacting with this GPU processor. So these are the broadly the different DRAM family: compute, mobile, and graphics. Again, for each one of the family, as I said, the power performance profile is different. Along with that, the features that are being supported is also very different. Because of that, the architecture, even though the fundamental cell is 1T1C, the architecture is completely different. Same thing like an SRAM where you have a 60 cell, right, in your SRAM. Even though we have SRAM 60 cell, you have different types of architectures like a register file, 1D memory, or like time division multiplex memory. So similar to that, we have the fundamental cell is 1T1C, but it comes with a variety of different architectures, features, and different profile. Let me also go through quickly on give a cartoon of this 1T1C cell. Now, the capacitor, if you see in the logic world or the ASIC industry, right, the capacitor is typically the way it is manufactured is through either like an MIM, it's a metal insulator metal capacitor, or we use the CMOS device as a capacitor. But the challenges with that capacitor is the capacitance is not sufficient. So what we do is we build a standalone capacitor using probably like you see these tall structures, the skinny and tall structure. This is actually a capacitor where you have like probably like metal insulator metal and or the dielectric. So these structures give very high capacitance, and beneath these capacitors you have this access device. This is what is the access device. These capacitors are very tall and skinny devices. In fact, you can imagine this more like an Burj Khalifa. Now, when we say like an 8 gigabit device, we have 8 billion such Burj Khalifas on one chip. So the biggest challenge is like imagine all these tall structures that are there. We need to ensure that they don't collapse. There is no any kind of electrical, physical failure, and each one of these devices work properly. That is one of the biggest challenge. Now, the way you can get more capacitance is like you can go really thicker cell or like really bigger cell on the cylindrical form. That the challenge there is like you want high density. Each component you want it to be like an 8 gigabit or 16 gigabit. So the bigger you make, then the lower the density that you get, right? You cannot accommodate so many capacitors in the chip. So we try to go skinny. Now, when you go skinny, you lose capacitance. So to compensate that, you go pretty tall in this vertical direction. Now, the challenge as you grow vertical is the aspect ratio becomes pretty high. And that is when you get like all kind of challenges on how you practically manufacture these capacitors. So here I'm just showing a glimpse of how these capacitors has emerged over a period of this last 10, 15 years, right? So starting from 110 nanometer all the way till like 1Z nanometer. So in the DRAM world, we don't go by this. Our scaling is a little different. We call it like 1x, 1Z, 1 by 1Z. And now we are at like mass manufacturing at 1 alpha. So this is the scaling node 1 alpha. The picture that I'm showing here is an 8 gigabit DDR4. And this is one of the most advanced DRAM in the industry. Let me go through the DRAM functional block and talk more about the blocks inside the DRAM. Before I talk about the DRAM, right? Let me first put what are the priorities in front of us. So the priorities is like ever increasing appetite for performance and bandwidth. We really need like very high throughput, very high speed DRAM, and along with that, we want it to be low power because we want the battery life of our mobile devices or our servers were in server form, which is like very power hungry. You want the DRAM to be low power so that you can reduce some of your costs there. Again, you want it to be low cost. The way you improvise on your cost is ensuring that your area of the chip is smaller. By that way, you can manufacture more chips in a reticle or in a wafer. And you try to improvise your yield. By that way, you will be able to sell more chips from your wafer. That's how you can make it low cost. In addition to that, nowadays the DRAM are getting like more complex. As I go through the function blocks, I can try to highlight some of the complexities in the DRAM because we are trying to integrate so many functions. It has become more like a mini processor now, along with an integrated memory. Because of all these challenges, the DRAM gives a lot of opportunities for VLSI engineers. Let it be whether you are in a digital designer or analog designer, IO, doesn't matter. It's one of the most complex memories that I have ever seen. So the way I see is like if you really get well versed with DRAM, then it means like you can really understand and work in any other memory relatively much easier because you get a full exposure of this 360-degree view of the different VLSI domain. That is very interesting for the engineers. Let me start with this functional block diagram of a DDR4. As we have seen in any of these memories, right? Any of the standard memories, the memory is like organized into different banks. Here you see this array of banks, bank 0 through bank 8. But let me first start with the interfaces. That is easy. So let me start with this command address interface. So these are the input pins. You have this clock bar, and then command address. So this is the input interface to the DRAM memory. And the output, what we get out of this memory is the data bits, which comes through this DQ. That is the IO interface for both reading and writing the data. Now, let me try to annotate here on how these interfaces are placed in an actual chip. Earlier, I was showing our DDR4 chip, right? 1 alpha 8 gigabit. So in that, this is what we have here on the spine of the chip is what we call as the periphery of the chip. In the periphery of the chip, we have this clock command address. All those pads are placed right over here. And then the DQ pads are placed where DQ pads are nothing but your IO pads. Those are placed on the other side of the periphery. On both sides of the spine, we have the array, and you see these very nice repeated structures. Those are your banks, memory banks. Now, the size of this chip is really huge. Depending upon the density and depending upon the technology node and depending upon the family, it can get as big as 100 square, which is like really big, very big chip. And that big chip throws out many challenges, and that challenges translates into opportunities. So let me start with the digital design. How a digital designer, what all opportunities are there in the DRAM for a digital designer, and I will take through the functional block and explain it. So for example, you have these input pins here, and the input pins, as soon as you get the command, you need to decode the command. Before you decode the command, you need to first latch the command and see like, hey, and then decode it, see whether it's a read command, write command, refresh, or power down, or so many different commands, right? So those commands are decoded, latched, and then decoded in the command address block. Now, let me explain a little more about this DRAM, right? DRAM is a pretty asynchronous memory. It's an asynchronous memory and very slow memory. Why do I say it's slow? Imagine we are talking about earlier in the slide, I said the capacitance of each storage cell is in the order of 10 femtofarads. And now you have this word line which is very resistive. So just to enable the word line itself will take several nanoseconds. It can take like 10 nanoseconds, 15 nanoseconds, depending upon how big is your word line and what PVT corner that you're operating. Whereas your clock frequency can operate as fast as like 500 nanoseconds. So imagine you give a read command, which is with a clock that is operating at 500 nanoseconds. And just to go and enable your access device, it takes 10-15 nanoseconds. And after that, you get the data, you sense the data, send it out through your data path. It might take like maybe 20-25 nanoseconds. That means you give your clock operating at 0.5 nanoseconds, and let's say your access time, which is like access time is nothing but you give a read date command, and when you get the read data out, it's 20 nanoseconds. It's very slow, and your processor cannot tolerate such high latency. So what we do is like we do a lot of stuff in our architecture to hide that high latency. So what we do is like, hey, we bring in this new feature called read and write latency. So what that means is like you give a read command and then you tell like, hey, my latency is like 40 cycles. That means after 40 cycles, you gave your command. That is when your first data is going to come out. Now, you can give back-to-back read command, consecutive read commands. By that way, you will start getting your data non-stop flow continuously, which you kind of hide your latency by kind of shifting your data out in the time, right? You give a read command, data comes after 40 cycles. From there onwards, it is continuous. To handle this latency shifting, we have internally latency shifters, which is kind of, you can think through like a simple shift register, right? So you get your command, you latch it, decode it, and take it through your latency shifters. Then comes your mode register. The mode register is nothing but like, now you want to tell like, hey, depending upon the operating frequency, sometimes you can tell like, hey, my latency is like 20 nanoseconds, which means 40 cycles. Now you are operating at like 1 nanosecond frequency, then you can make your read latency as probably 10 cycles. So all these features with which you want to operate your DRAM is registered through these mode registers. That is what is mode register. Now, if you see here, you have this refresh counter. Let me quickly talk about this need for refresh, right? So the DRAM cell, which is storing the data in a capacitor, your capacitor is very leaky device. we know that we lose charge through a capacitor, and then you have this access transistor. Access transistor, there is like subthreshold leakage. Because of all those reasons, the data continuously leaks from the storage cell. So what we need to do is we need to periodically refresh the cell. So when you refresh the cell, that is how you make sure you don't lose the data as long as the data is as long as the memory is powered up. In order to refresh the cell, we have to go through certain protocols. There are certain refresh protocols. How often do you refresh? Which depends upon your leakage, which in turn depends upon your temperature. So if your temperature is high, we know that like the transistor leaks more. So at high temperature, we refresh often. At low temperature, we refresh less. So to give some specification, right? At high temperature, let's say at 125 C, we may probably be refreshing every 32 milliseconds or 16 milliseconds. So the controller, which interacts with the DRAM, smartly handles how you are going to interleave your command, like you're giving a read-write operations with this refresh operation in such a way that your processor doesn't see this refresh as a burden, because every 64 milliseconds you have to go and like activate all your rows, refresh your data, which might eventually become a burden to the processor, right? During that time frame, you're halting your operation. But nowadays, there are a lot of algorithms in place where the controller kind of hides this refresh operation such a way that it doesn't become big onus on the processor side. That is what is the refresh. And I would also like to talk about the clock domains here. Now, the data that we are sending out of the DRAM, which is coming out of this DQ, this is source synchronous. What source synchronous means, along with the data, you send out the output clock, which facilitates the controller to capture the data that is coming from the DRAM. So that is what is called the DQS. Then the system clock, that is the clock at which the entire system operates. That is like placed over here. So earlier I said this chip is very big. It's like as high as 100 mm square. Now you have your clock and command address, which is placed on one side of the chip, and then you have your DQs that are placed on the other side of the chip. Now we don't waste any space in between. Just the sheer number of pads that are there, including with the power supply. If we start from here, we serially place these pads, and then probably it will extend to the other end of the chip. Now, what is the big deal about this? We just placed all these pads right next to each other, right? The big deal is the time that takes just to propagate a signal from one end of the chip to other end of the chip will take few nanoseconds. Let's say you have a system clock here, and then you want to just propagate to your DQ so that you can just capture the data. That takes several nanoseconds. That is challenge number one. The second challenge is we need to say like, hey, your system clock is very tightly aligned with your DQS clock. Now, these are spatially located far apart. To just give an analogy, right? Let's say if you're from Bangalore, you can think of this like the clock is like at Hennur, and then your DQS is in Silkboard. Or if you're from Hyderabad, you can think of it as clock is in like probably Cyberabad, and your DQS is in Shamshabad. Now we are talking about traveling from this from your Hyderabad to Shamshabad, and make sure they all are aligned in time. That means when you hand the system clock that is handshaking with the DQS clock, we always tell that like it's very well aligned. That means what we are saying is, hey, let me launch my clock from this end of the chip, and when it reaches the other end of the chip, I always need to make sure that the DQ is aligned with the clock over here, which is very challenging, right? When the distance itself is in the order of several nanoseconds, how are we going to make sure that these clocks are overlapping? To facilitate that, we have clock domain crossing circuits. That is what we call it as DLL, which is delay lock loop circuit. Essentially, that ensures your system clock is phase aligned with your DQS clock. And by the way, the DLL itself is one massive big circuit. Sometimes, depending upon the applications, we use a DLL or we can use a PLL. Along with that, the DRAM, when it gives out the data, it gives the data in both rising edge and falling edge. And we need to ensure that the duty cycle of the DQS clock that we output is 50%. Then you need a duty cycle corrector, which again is a massive digital block. Let me, interest of time, let me quickly go through some of these blocks because I just want to highlight other domains also. Earlier I was saying like, hey, the DRAM has become so complex. I said like a lot of functions are being integrated. So one among them is what we call it as a training. Let me give a very simple example of training. Let me talk about VREF training. So VREF is nothing but like when you have your data, the incoming data, which is like 1 unit cycle is like half the clock frequency. Now it's single-ended, which means in order to capture your data, you need a VREF signal. Earlier, in previous generations, the VREF was sent by the controller. The controller, along with the clock and the DQ, to say, hey, here is the VREF. Nowadays, the VREF is generated inside the chip, on chip, which when we generate the VREF inside, because of this high frequency of operation, the VREF, and along with the termination, I'll talk about the termination in a minute. So the VREF can be like, it is not always VDD over 2, VCC over 2. Sometimes it can be 0.75 VCC or it can be 0.25 VCC or some other range, depending upon how you have terminated your DQs. Since you don't know what is the optimal value of VREF, you do this training where during the training, the DRAM handshakes with the controller and says like, hey, can you tell me if my VREF is optimal? So in order to do that, the controller will send some data, data that is known to the DRAM, what it is going to send and what it is going to receive. So we say, hey, okay, set your VREF at one point, see if you are capturing the data well. And then whatever the data you captured, you send it back to your controller and say, hey, this is the data that what I received. Is this what you launched? So then the controller will say, oh, no, this is not what I launched. Then you move your VREF. So you do this back and forth process of communicating between the DRAM and controller, sweep the VREF and find out what is the optimal VREF value for that PVT condition. So this is a training protocol that happens when you power up the chip. And in order to do that, you have a lot of VREF related circuits that are on the chip. Along with that, I said about like this 8 billion Burj Khalifas, where we say, hey, each and every one of these pillars, we need to ensure that it's working properly. You don't have any single bit error. To do that, what we do is what we have on the chip is like we have many redundant elements. What these redundant elements does is like whenever there's a failed row or column, we go ahead and replace that failed row and column with a redundant row or column. In order to replace that, you need fuses and you need to check. Sometimes we check through a test or probe, or we can also do this test with an inbuilt BIST. So we have an on-die BIST in the memory, inside the memory. So now you can understand how complex your DRAM has become, because in typical memories, what you have is like a command address, latch, decoding, shifting, all this kind of stuff, right? Along with that, now we are talking about training sequence, handshaking between the controller and the memory. We are talking about on-die VREF generation. We are talking about on-die DLL, duty cycle corrector, all the DFT mechanism, BIST, redundant elements, and we also have ECC, on-die ECC, because we cannot tolerate single bit errors. So to improve your RAS, RAS means the reliability, addressability, and serviceability of a memory. So improve your RAS, we have on-die ECC. So these are some of the opportunities for the digital designers. Whenever you see, hey, wow, I have studied this in my course. I know what's an counter. I know what's an oscillator. I know what's a multiplexer, FIFO. Now you can put all of them into use in a DRAM. So let me go to the next part of it, the analog design, right? So initially, when I was talking about the priorities, I said low power. So in order to save power, what we do is like we internally regulate the supply. Now, when we regulate the supply, let's say your external supply is 1.5 volts or 1.2 volts, then you regulate internally to 1 volt. That means you need a reference generator so that you can regulate your supply from 1.2 to 1 volt. To have a reference generator, you need to have a band gap. So now we have an on-die band gap, on-die reference generator, on-die regulators. Along with that, we have all these bias supplies, the bias generators. Now, this is for one supply. Like this, we have at least 10 internal supplies. Then the question comes, hey, why do you need 10 internal supplies, right? So let me go back to my initial slide here. Earlier, I said it's a 1T, 1C cell, right? And it's an NMOS. We all know that NMOS is not a good conductor of a 1. So if you want to store a full 1, you need to boost your gate voltage. So if your supply voltage is 1, and let's say your access device VT is like, let's say 1 volt or something like that, then you need to boost this up to 2.53 volts so that you have sufficient margin. That means you need to have an on-die charge pump to boost the word line to 3 volts or 2.5 volts. So that adds another supply. Then I said about refresh. So to reduce the leakage, we bias the substrate at a negative voltage. That means you need to have a negative charge pump so that you can bias the substrate. Now, biasing the substrate alone doesn't mitigate your leakage issue. What we do is the off-word lines, we take it negative supply. So you need one more charge pump. Then the common node is biased at VCC over 2. That means you need another regulator. So here itself, I talked about power supply, internal main power supply, which is regulated. I talked about word line supply, both positive and negative. So that makes 3. Substrate makes 4. This common node biasing makes it 5. Along with that, we have a lot of other internal circuitry which we operate at different supplies, which means we at least have internal supplies. We have probably like more than a dozen of them. That means as an analog engineer, let's say you have taken this analog classes and then you see like, hey, wow, I studied about band gap, I studied about the LDOs, I studied about push-pull. Now you can put all of this into use in a DRAM because of all this. Now, I also talked about temp sensor. I also talked about refresh rate. The refresh rate varies depending upon the temperature at which your DRAM is operating. Sometimes the temperature can be at 125, sometimes it can be 85, 25. Let's say you are from Sweden, then probably like the initial operating temperature is at like a winter, it's like negative. Or let's say you are from Chennai, then even at a good day, probably it's like starts with 45 degrees or 40 degrees. Then internally, the temperature goes very high. So irrespective of the place and or you're in taking to a space, then the temperature is pretty cold. So now, depending upon this temperature range that you're operating in, you internally modulate your refresh. That means you need to have an on-die temp sensor. That again is another complex analog block, right? You have a temp sensor, you have band gap with the PTAT and the CTAT. Then you have to reduce your power. Then you can your data buffers can be like a current mode logic. We have on-die charge pumps. reference generators, calibration circuit. So let me quickly touch upon the calibration circuit. So earlier I was talking about the termination, right? So maybe it's a good time I should talk about the package. Now let me talk about IOs so that like we can quickly talk about termination. So we have the IOs to reduce your power. You probably reduce the swing of these IOs. It's become small swing, and then it's operating at very high speed. So you have a complex receiver and a transmitter. When you're operating at like, let's say, with 300, 400 picoseconds clock, and you're capturing this data, which is like a 150 or 180 picoseconds, your receiver becomes super complex. You need to have a DFE, which is nothing but a decision feedback equalization, or you can have a CTLE, continuous time linear equalizer. So now you see how big complex your IO has become, operating at high speed, operating at low voltage. Now that throws in a lot of challenges related to signal integrity, right? To improve your signal integrity, you terminate your DQs and terminate your command address. What is this termination? So quickly, I'll take a minute to talk about termination. So now, many of us enjoy playing in a wave pool, right? In a wave pool, when you're in a wave pool, you see like the waves that are coming in, hitting you at the end. You really enjoy it. Now, the waves get hit the other side of the wall and then reflects back. And depending upon the phase or the amplitude, it may hinder the incoming wave, or it may make your incoming waves even amplify your incoming waves, right? In a wave pool, you see this, and we really enjoy it. But when it comes to your IO design, you hate the reflections, because your reflections are uncertainties. You don't know, it interferes with your incoming data. So you terminate it. So what termination means, instead of being in a wave pool, what you do is you open up the wall so that the water that goes and falls like a waterfall, smooth waterfall. There is no reflection back. That is what you do in design. In DRAM design, you terminate it so that there is no reflection back. Now, for that termination, which we call it as a ZQ, you need to do a lot of calibration. So that now you can see what kind of opportunities that it throws to your IO designer, where you are designing these complex receivers and transmitters with on-die termination and ESD, all this kind of interesting circuits on a DRAM side. Now, since we are there at the IOs, we talked about the analog circuits. Let me quickly talk about the package. Depending upon the compute family or graphics family or like the mobile family, the package is completely different. The run length of this, the DQs or command can run several mils. When it is running several mils, then as a package designer, you know what kind of complexity it is. Or in a mobile, you have this package on package. That means like that you now you can think about like, hey, how do I even make sure at a system level it's operating well without any of these power delivery network challenges or signal integrity challenges? Or how do I ensure that when we are building this 3D chip, how do I ensure I'm driving this TSV from one chip to other side of the chip without any signal loss? So that kind of throws out opportunities for the package and module designers. Now, I'm sorry, I'm just rushing up here. This is something I'm not trying to give you this intricacies of a DRAM, but I'm just giving you the overview of how a DRAM operates. So just going a little faster. Let me talk about the memory array design. Earlier I was saying like, hey, your memory is like organized into different banks. Then you have these row addresses. Then you have this column decoder, sense amplifier, which are all of this is highlighted here, right? Now, we know that the memory cell is 1T, 1C. What kind of challenge can there be to just design a 1T1C cell, right? Honestly, it is one of, again, very complex to design even that 1T1C cell. Let me tell you why. You have this 1T1C cell in your core. Now, we know that we need a sense amplifier to sense the signal, which I said earlier, it's like less than 100 millivolts, right? So you need to have a little complex sense amplifier. The sense amplifier will be like at least some 20 devices. So in this pitch of 1T1C, you have to lay out the sense amplifier, which has 20 devices. Now imagine how we are going to lay the sense amplifier in the pitch of your 1T1C in the word line direction or your digit line direction. Now that you take and then you send out the data from your array to your periphery, it has to go through multiple stages of sense amplifier, buffers, the multiplexing. All of it is like throws out a lot of interesting challenges, which honestly, I feel as a DRAM designer, I have been in this DRAM world for like more than a decade or like close to 15 years now, just on the DRAM, and I learn every day. The domain that the challenges and the opportunities that it throws out, let it be in digital or let it be in analog or IO package, the custom logic, we learn a lot of things every day. And that is the reason why I was earlier saying like, hey, once you understand this DRAM thoroughly, then all other memories become relatively easy to understand because all the complexities are embedded in this DRAM now. So I thought I talked about the mode registers, refresh, the memory array I talked, row and column, the read path I didn't touch upon, but that is the data path. And then I talked about the on-die termination, and then the data goes out. So this is a very simple, quick taking through the functional block of the DRAM. I also talked about the package, different modules. Okay, so let me just, hey Kalyan, are you going to talk about Micron? You have a...
No, Venkat, you can go ahead. I don't have that.
Okay, okay, probably let me quickly talk about Micron. So Micron is the fourth largest semiconductor company in the world. And we are number one in automotive supplier. Automotive memory, we are number one, and same in graphics memory, we are number one. And we are a technology leader in both DRAM and NAND. My colleague Kalyan is going to take through this fantastic the NAND world. So he will give you about all the fascinating stuff happens in this NAND domain. We are the technology leader in both DRAM and NAND world. We are the first to market the 1 alpha node and 176 layer NAND flash. Along with that, Micron, the fundamental philosophy of Micron is innovation. So innovation is what has driven this company, which is 40 years old. Even though we are like a baby at India, we are just crossed our 3 years. We are like a 40 years old company. Our legacy is like innovation. I have put here different timelines, and each and every timeline you can see all the innovative stuff that we have delivered to this market. And we are leaders in mobile chip as well. We are the first one to support a 6400 Mbps speed 12 GB die LPDDR5 with UMCP. That's like an the flash controller, universal flash storage controller. When it let it be, so typically let it come to be performance, power, or technology node advancing, Micron is on top of the game. We also have an extensive portfolio of DRAM, flash storage, and AI accelerators. So we have this end-to-end portfolio of memory, storage, and AI accelerator. When it comes to DRAM, we have this DDR5 compute memory, LPDDR5 mobile memory, GDDR6 graphics, and HBM, high bandwidth memory. Same when it goes to flash, starting from 3D NAND flash to QLC, to the world's most advanced 176 or 196 layers. We are the most innovative company. With that, let me end my topic on DRAM. Any questions on DRAM before I hand it over to my colleague and my friend Kalyan?
So Venkat, can we take questions at the end?
Ashutosh, I'm sorry, I have another appointment. So okay. Unfortunately, I have to take the questions now. Sorry about that.
Let's take one quick one before we start with Kalyan, right?
Perfect.
One of the questions that has come across is in present day mobile memories like DDR4, which transistor number DRAMs are used? 1T, 2T, 3T, 6T, or anything higher?
It's 1T, 1C cell.
Okay. And another one that has come up is a DRAM engineer designs all the analog and digital blocks, or is he or she going to use blocks developed by different teams?
Well, imagine the DRAM chip is so complex, there is no one engineer who can design this entire DRAM, right? So our team, we have probably like each team, DRAM team is like 100, we have more than 100 engineers in each DRAM. So each engineer owns a block and then we design and develop internally in-house. So I'm assuming the question is, do you get the IP from third party and then we integrate it? No, we in-house develop all the, whatever I showed, everything is in-house developed.
Got it. That's pretty much it, Venkat. Thanks for your time.
All right.
Since you have an appointment, please go ahead. Kalyan, over to you for the next part of the tutorial.
So first of all, thanks for giving me this opportunity to interact with students is what I believe is most of the audience, and any other engineer or technologist who is present as part of this conference, VLSID conference. And thanks a lot for VLSID team to invite Micron as well as myself to be able to be part of this conference. So with that, let me start my presentation. I am the counterpart of Venkat Bringi. My name is Kalyan. So if Venkat does the DRAM, we do the NAND flash memory design. So I am leading the NAND flash design unit here in Hyderabad, India. So today, I'm going to give a quick tutorial about the NAND flash itself. So throughout this tutorial, you will see some of these abbreviations being used, like SLC, it stands for a single level cell, MLC for a multi-level cell, so on and so forth. So better to have them at the back of your mind, if you can quickly go through them. But okay. As far as the agenda itself is concerned, I will introduce you to the nature of the NAND flash memory. Then we talk about the planar SLC NAND, the basics of NAND flash, like what a read operation is, what a program operation is, what an erase operation is, and how do I estimate performance in NAND flash. Then I move to the 3D NAND, which is now the current state of art as far as NAND flash technology is concerned. I'll quickly talk about the floating gate technology, the innovative CMOS under array technology that Micron uses, a parallel plane operation, which here in this case is like a 4-plane operation, and evolution from the floating gate to a new technology called replacement gate that is now the state of art. Finally, some discussion about the triple level cell technology. We'll quickly show how the TLC program looks like, how the TLC read looks like, and operations for data recovery. Okay, so if we just look at the memory hierarchy and the NAND applications, NAND has a great diversity and to cover a wide range of memory hierarchy. So on the left side, you will see price per bit. Okay. On the right side, you see access speeds. And now the horizontal line is nothing but the bit demand. So if you actually see, if you take an SRAM or for that case, DRAM also, right? The access speeds are pretty high. But if you look at the price per bit, it is extensively high as compared to the other memories that you see. On the bottom of this pyramid or rectangle, triangle that you see here, we have the hard disk and magnetic type memories, which are of magnetic nature. You can see the access times are pretty high, greater than a millisecond. So, but the price per bit is actually low. So it is like, a competition of lower the price versus access speed. The higher the access speeds, the higher the price, and vice versa applies. So now if you see, where does my NAND come in, right? NAND is now a compromise between high speed and price. So you get sort of the best of both worlds. So if you see the access times, yeah, they are of the order of microseconds. But if you see, the price per bit is also going low. Today we are talking about flash also trying to replace the hard disk. So we are bringing the price down to such an extent and make it so competitive that and if you can already see the access speeds are pretty good when compared to a magnetic tape or hard disk. So by bringing down the price, we are trying to go into this application where we can actually replace the hard disk. Okay, so so NAND is an animal which gives you the best of both worlds: price, access, speed. Okay, then you have other storage class memories, which are nothing but the phase change memory and resistive RAM. So here, yeah, these have been touted as futuristic technologies, which can actually replace NAND maybe in future. But till date, on a volume scale, they were they were not able to compete with NAND, or they are still in the evolution phase. But NAND, we are still able to continue to scale and outclass or outrun both PCM and RRAM at this point of time. Okay, that now let us look at the diversity of NAND flash. So what Venkat was showing is like 1T, 1C transistor, right? Here we will have, you can imagine, all of you are engineers in the electrical engineering domain. So you can easily visualize a NAND gate. It has like a 2-input NAND gate, has like a 2 NMOS transistors in series. So you can correlate that each NAND device there in our technology is sort of a storage cell, which is nothing but equivalent to the capacitor that Venkat was actually showing before. So contrary to one unit having just one cell in a DRAM, we have stacked cells. Here you can actually see the word lines are all encircling something like a cylinder. The intersection of the word line and the cylinder forms actually a storage node. So now you have storage nodes in a 3D stacked vertically on top of each other. So you're looking at these very nanometer geometries which are trying to hold electrons or charge as part of data storage. You can imagine having charge implies you stored a digital 1. No charge implies a 0. It's a simple way of understanding how a NAND flash works. In the planar NAND, you can actually see all the word lines are all horizontal. The green rectangular bars that you see, they're all horizontal. And you can actually see, if you see the orange perpendicular lines are the bit lines. So the intersection of the green line and the orange line, it forms a storage node. So all the storage nodes are in the one plane. That is why it's called a planar NAND. In 3D, you are actually stacking up word lines vertically. So you can see these are all rectangular plates now, and now the cylindrical structures or the green lines. If you see the green lines, which are nothing but the bit lines, they are running perpendicular to the word lines. So the intersection of the cylindrical structures with each of these rectangular word lines, plates, is nothing but a storage cell. So pretty complex design. Huge challenge to hold data into these small structures. So now if I just talk about how does NAND design compared to the DRAM design, Venkat gave you an idea of what all circuits are there in the DRAM. He talked about IO circuits. He talked about analog circuits. He talked about digital circuits. All of these pretty much apply. Like in the analog, he talked about charge pumps, band gap references, everything. So all of these pretty much apply to the NAND flash as well. So any budding analog or digital designer or a IO or interface designer, he has plenty of opportunities to explore in NAND flash as well as DRAM. Pretty much the external periphery circuits are more or less the same. What differs is the array. So where it was a 1T, 1C transistor, single transistor, we have a stack of memory storage nodes, which makes it much more complex to hold data onto. Okay, what are all the different versions of NAND flash uh, technologies that we have? We have a SLC, is nothing but a single level cell. You can imagine having charge as a 0 and not having a charge as 1. So that is like on the charge storage node. So that is the simplest single level cell. But if you are able to distinguish the charge, let's say charge is nothing but you can look at it as like electrons, right? If you are storing somewhere like 2 electrons, you let's say no electrons, let's go for the MLC. Let's say no electrons is 1 1. Okay. Now you say, let me say I am able to store 4 electrons, and in another cell I'm able to store 8 electrons, and in another cell I'm able to store 12 electrons. So no electrons implies the cell was storing 1 1. You can categorize it that way. 4 electrons implies digital equivalent is 1 0, 8 electrons is 0 1, and finally 12 electrons is 0 0. So by changing the number of electrons that you are able to store onto the charge storage node or the cell, you are able to create a multi-level cell, which can be like a 2-bit per cell or a 3-bit per cell, which is a TLC or a QLC. What you see is in each of these, like say compared to an MLC, when you go to a TLC, the gap between these distributions, let's say in the case of a TLC, the gap between 000 and 001 is much smaller. Whereas in a QLC, it is even worse. The gap between each of the distributions is much worse. What it means is, if you take the cost, because, okay, let's go a little bit slow in this. Compared to an MLC, if I want to store in 2 cells, if I have to store a data 0 1, I will have to use 2 cells. One stores the data 0, other stores the data 1. Now, if I take an MLC, I'll be able to store the information 0 1 in a single cell, which means the area occupied by an MLC is lesser than the area occupied by SLC. So my the storage unit is smaller, which means I save cost. So from SLC to QLC, if I go in the X direction, I will reduce the cost. But reliability goes down because the spacing between the distributions is smaller as you go from left to right. So they tend to overlap faster and data becomes unpredictable faster. Similarly, performance, actually in SLC, if I want to read data in a cell, I can just read between the 2 cells and then I will say the data is 0 or 1. Whereas in an MLC, it can be any one of the 4. So I'll have to do 2 reads to actually figure out what the data pattern is. So the number of reads actually increase when you go from left to right. So the performance actually is degraded as you go from SLC to a QLC, but QLC gives you the benefit of lower cost. And as you all know, in a memory world, it's all about how much space you take to store data. And there are nowadays there are system level optimizations which can be done to mitigate the difference of speed between an SLC and a QLC. Okay, with that, let's go to a simple planar NAND structure. As I said, here you actually see there are several word lines, right? This is a simple one string of a NAND where I have 8 storage cells. Word line 0 to word line 7 are indicative of that. And then I have a drain, which is nothing but the bit line, and a SRC, which is nothing but the source. And I have the select gate drain and select gate source transistors, which connect my string to the bit line or the source. Now, this is nothing but a simple cell. You see all the cells, like just like in a NAND gate, they're all connected in series. Okay. If I look at like a planar NAND cell array, this is how it looks. You have word lines, all the word lines in one plane, and then you have SGD and SGS connecting all the parallel strings, if I call them, connecting them to the bit lines or the source. So once you enable SGD and the SGS, all the strings are connected to the bit lines or the source. Okay, so all of them are in the same plane. Okay, so if you want to do a read operation in a NAND flash, as Venkat was also talking about reading from the array, you require sense amplifiers. So we have inbuilt sense amplifiers for someone who wants to work on the core. Now, if I want to figure out this particular cell, which is highlighted in blue, what data does it contain? Is it a bit 0 or a bit 1? What I do is I figure it out through a read operation. What we do is we turn on all the other transistors, right, fully. And now I apply a voltage which is between the 0 and 1. There is a spacing between the two distributions. So I try to apply a voltage in between and try to read. If there is, if this particular cell contains data 0, implies the voltage I applied on the gate or the word line is lesser than the voltage of the voltage on the cell due to the electrons. So it would not contain. It is like, you can imagine the transistor has this VGS, which is less than the VT. So there is no current conduction in that string. If it has a data 1, my VGS is greater than VT, which implies the cell conducts and you see a current. So having a current versus no current, you will be able to distinguish and tell whether the data is 0 or 1. That's a read operation explained in the simplest terms. Now, if you see, what we do is to have more parallelism, we read multiple, across the word line. If you look at it, this is my word line direction. So along the word line direction, all the cells are read in parallel. So if you see this cell, and this cell, and this cell, they're all read in parallel. So all the word lines, all the cells on a particular word line, they form a page, and all of them are read in parallel. And the data is read and stored in sensams, and the sensams detect the data, and now from the sensams we send it out to the external world. Now, how do I program? If you have read about the basics of a NAND flash, it is mostly about creating a huge electric field between the gate and the channel. And when you create this huge potential difference between the gate and the channel, the electrons from the channel tunnel into the storage node. So if you see, there are 3 in this highlighted cell, you can see 2 green rectangular lines sort of thing, rectangular shapes. So the one on the top is actually called the word line, or it's called the word line. So the second green line is nothing but the storage cell. That is nothing but where once you apply a huge potential difference on the word line, and the orange channel of the transistor, you apply a 0, you create this huge potential difference for electrons to tunnel from the channel onto the storage node. That's how you program. So you apply higher voltage, more number of electrons tunnel. That's where you create this different states. So I say I only want to create 4 electrons. I'm just giving for an example in the sense. I will only apply say 20 volt. Now I want to get 8 electrons to create a different state. I beef up this voltage. I will make it 24. So you see there are a huge number of voltages that you need to actually do that, right? So similarly to what Venkat was mentioning, you have these internal charge pumps which regulate and generate these different voltage patterns. Like say you see a 2 volt here, a 10 volt here, a 20 volt here. All of these voltages are internally generated and applied to the NAND string to be able to program or read. Okay. And now if I don't want to program, right? So programming implies here my data is 0. I'm placing electrons there. Now what do I have to do if I don't want to program or I want to have a data 1? So having a 1 data, I'm saying I will not program, I will not store any electrons on that. So how do I do that? As I was talking about, the tunneling or the electron movement happens when you create this huge potential difference. So what do we do here is by floating the bit line, or like we will cut off the channel, right? By applying an initial voltage on the SGD transistor, we cut off the channel. So the channel, when you are ramping up the, like say on the word lines, like say 10 volts or 20 volts, it couples up. So you have something coupled up with a coupling ratio. So you have 20 volts on the word lines and 8 volts on the channel. So contrary to this one where you are actually programming, your bit line was at your channel was at 0 volts. So you have like 20 minus 0. That's the potential difference that you have. Here, if you see, the electric field is reduced quite a bit, which means the electric field is not enough to actually cause tunneling. So you will not have any electrons stored on that charge storage node, which is nothing but your 1 data. Now, a page program operation is what is how you attain parallelism. So what you're saying is what we are saying is you apply 20 volt on the word line, right? Where if I want to write a 0, I pass 0 volts onto the channel. If I want to not program, I apply 2 volt and I float the channel so that the channel corresponding to that cell in question couples up and doesn't program, whereas the one which is getting a 0 on the channel gets programmed. So that's how you program data. So the user here in this case across this page horizontally has given the data 0101. So that gets programmed into the cells in question, and you will read that back through a read operation when you want to pass the data back onto for the user. So contrary to a DRAM, NAND flash is non-volatile. So you will not lose power once you remove the power plug. So you will have the data retained, and we promise that that will come with the spec that you will be able to successfully read data for X amount of time. How do I erase? So now, for example, you can say the most common application for a flash memory or NAND flash is you put it into your mobile for storing songs, right? Now I want to change the song. How do I do that? I have to erase the stored data. I cannot change data on the fly. I have to erase the block first, or they erase the string first, remove all the data that it has, and reprogram new data. How do I do that? I reverse the program operation. So if you remember in program operation, I was applying high voltage on the gate. or the word line like here, and I was forcing the channel to be 0, you will exactly reverse that one. Here you see the channel or ATUB in this question, in this case, is actually getting 20 volts. So you pass 20 volt onto the channel. All the word lines get 0 volt. So you reverse the field so that electrons, if at all any of them are stored onto the charge storage node, they tunnel back and go back to the channel. So it is just the reverse operation of a program. So that is how you actually erase the data, and now your string is actually available to store new data. Okay, this is the block erase operation. We, because of the difficulties in associated with circuitry, we do not, unlike program, we do not like program data, like in program we program data on per page basis, whereas erase happens on a block basis. You erase all the data in one block at one shot. And how do you do that? Bit lines are all going to 20 volt, word lines are all going to 0 volt. You reverse the field and do the reverse tunneling. This is a memory array diagram. So you can imagine the entire block diagram shown by Venkat, except that you remove the array portion from DRAM, you plug in our NAND array. So the cell array or the NAND array is, you can imagine this bigger rectangular cube is nothing but your NAND array. It consists of several blocks, and within each block, one word line is nothing but a page. So that is the smallest unit for read and program. But you erase on a block basis. So the array will have multiple blocks, and you can have multiple arrays. Now, the sense amplifiers that I was actually talking about, through which data comes in or data goes out, is what we call the page buffer. So external world pumps in data 0101, that 0101 data comes into the page buffer. From the page buffer, it is programmed into the cell array. And as and when the user needs the data, he can, from the cell array, do a read operation, get the data onto the page buffer, and from the page buffer, serially data is passed out onto the DQ pad. So this is nothing but serial data in and serial data out is nothing but the IO or interface or the DQ part that that Venkat actually showed. So all the Z calibrations, all those things do happen in the NAND as well. Now, as I was showing, there are several strings, right? Your wall, we have in a typical page, we have 16 kilobyte strings. So what I'm trying to say is, if I say I'm providing, I will be able to accommodate 16 kilobyte of user data per page, right? That is my promise to the guy who buys my memory. So, but when you are talking about these extremely small lithographies, you or the process may see some strings which are defective. So to accommodate for that, we provide something called spare bytes, spare bytes along with the ECC bytes. I'll come and talk about the ECC bytes later. But what these spare bytes do is, if a particular string happens to be defective, that particular string is replaced by a spare byte. So based on the process maturity, if my process says out of every 16 kilobyte, my defective strings will not be more than, let's say, 16 byte. I will have to provide 16 byte spare strings. And on top of that, I also need error correction. We will get to it as like why we need error correction. So as I said, when the distributions become so tight and they start to overlap, there will be intrinsic errors. So these ECC bytes are essentially used to store a ECC code sort of thing on a per page basis. Compared to what DRAM has, we used to have the ECC inside the NAND die, but now because of space restrictions, we threw the burden on the system. So, but internally on a per page basis, we allow the user or system to store some ECC code relevant data or a key, which can be used to effectively decode the data in case errors are there in the 16 kilobyte user data. So performances actually. So read, as I said, on a per page, you from the previous diagram, you will be able to read about 16 kilobyte user data plus 2 kilobyte ECC data. That data transfer happens from the page buffer, from the array to the page buffer in about 35 microseconds. After that, the data is serially clocked out, and it happens with 1 nanosecond cycle. So if you do the math for 16 kilobyte plus 2 kilobyte data, that is about additional 18 microseconds to clock out the data. So what it means is approximately 54 microseconds is required to retrieve 16 kilobyte page data from a user standpoint. So the read performance is essentially calculated by the effective data divided by the total time it took to read out the data. So that is about 306 megabytes per second. Okay. So for the program operation, similarly, you are programming 16 kilobyte user data plus 2 kilobyte ECC data from the external world. User clocks in the data to the page buffers in about with 1 nanosecond cycle, which amounts to 18 microseconds is what I talked about. And now you go back and you do the program operation by applying high voltage on the word lines, and based on the data, you either hold the channel to zero or float the channel on across the different strings. That typical program time is about 150 microseconds. So if you do the math again, and NAND program performance is about 97 megabytes per second, right? So if you want to edit the data, as I was talking about, you cannot say, you cannot dynamically change from 0 to a 1 or a 1 to 0. You have to clean up the slate, change all the ones to all the zeros to 1, which is nothing but erase state, and then you have to reprogram your new data. So if I want to edit data in a page, the first operation you need to do is you need to read the data so that you retrieve all the data in the associated block first. Now, erase operation, where you do the opposite to clean up everything, is about 2 milliseconds. And now you get your new data and reprogram the data. So it's about 16.2 milliseconds whenever you want to change the data in a page. Pretty expensive operation. Okay. Now this is what I was talking about, ECC and randomizer. So we have the ECC encoder in the chip. So what it does is it is nothing but a key. It takes the data from the host and it does the ECC encoding. And then we also go through a randomizer. What we see is there are like some patterns which actually cause, if you do not fully randomize, right? When I say randomization is like, if you don't randomize, what happens is, let's go for this TLC distribution or MLC distribution. If you do not randomize, you might have out of 16 kilobyte data, if the user just gives 8 kilobyte 00 data and 8 kilobyte 11 data, you will not be able to effectively use all the algorithms, or there will be a lot more interference because of the movement required. That specific details is beyond the scope of this presentation. But what the randomizer does is, if user has 16 kilobyte data that he wants to program into the flash, it will take the data and randomize it such a way that the data that goes into the array is having equal distribution across these 4 states. So 00 will have 4 kilobyte user data will be 00, 4 kilobyte user data will be 01, 4 kilobyte data will be 10, and 4 kilobyte data will be 11. So it's a pretty complex algorithm, but without randomization, it is very difficult to promise that you will be able to retain or like the sanctity of data inside cells cannot be guaranteed to for the specification we promised inside at the data sheet that we give to the user who buys this NAND component. Okay. So now we go to the 3D NAND. 3D NAND, we just took the planar NAND and we made it like stand up. So now because you're going the contrary to like increase, if you want to increase the number of the storage, previously we were increasing in 2D NAND, we were increasing the number of word lines, right? So that is how you increase the. So in a planar NAND, what happens is if you say X and Y, the Y dimension continues to increase, which can hit the packaging limits, right? And in a mobile, if you say if you give some area for storage for the flash storage, now if you increase the X, it will start eating into the area available for other circuits. Now by just flipping the element in the vertical direction, and now your word lines are growing up in the Z direction. So the other way to look at it is now your package height is the cause of concern, but as long as you don't hit the limit for the packaging in the Z direction, you have a lot more scope to grow. So that is the beauty of the 3D NAND. Now you are saying, okay, all my strings are vertical, so my vertical, and I am able to stack all the word lines in the vertical direction. Now, if you see, I have my array here in the picture, the word lines, active word lines, SGD, and the bit line and the metal layers on the top. Now, underneath the array, whatever space I have, we are using that space to build in the periphery circuits like charge pumps or band gaps or so on and so forth. You can imagine this as like, say, one floor of my apartment complex is my one block, right? Or one word line, you can imagine. Now my second level or second level is nothing but my second floor, and third floor is nothing but my third word line. So you are, each level is one word line, right? And now if you want to increase the memory capacity, you just increase the number of blocks in your apartment in the Z direction. Now your cellar area is actually empty. That is where we have started placing the peripheral circuits, which is called the CMOS under the array, in very innovative technology, which is actually an area saving process. And it gives you die size saving, because now if you look from the top, all you see is the array. So your die X and Y are smaller. Okay. So this is the memory tile with CMOS circuit. So if you see, these are all the, these are all the blue lines are all the bit lines. Then you have the physical blocks, horizontal bars in green. Under the blocks, you're actually placing your CMOS circuits. And so that, in the 2D NAND, you had to place all the circuits, or the planar NAND, all the circuits were needed additional CMOS space after the string drivers or after the 1 kilobyte page buffer that you see. So pretty innovative technology, and pretty good in terms of cost savings. So this is a typical die floor plan. Okay. So plane 0, plane 1, plane 2, plane 3 are nothing but the different banks. So imagine you are looking at it from the top. So underneath you will have all the CMOS under array circuits. Then you have the DQ buffers and the bonding pads. The bonding pads are nothing but the DQ pads that Venkat showed. You will be able to clock in data and clock out data. Okay. So multi-plane operation. So if I say, if I want to improve my throughput, instead of just programming 16 kilobyte to a plane 0, here in a 4-plane program or 4-plane read, what essentially I'm doing is, let's take 4-plane read. I am reading data from 4 planes parallelly. So by multiplexing them or doing them in a parallel fashion, previously when my performance was 16 kilobyte in X amount of microseconds, if I read 4 planes one after the other, it will be like 64 microseconds. Sorry, 64 kilobyte in 4x microseconds. Now, by making them parallel, I would not be having to do 4x. I would not have to wait like 4x the time to read 64 kilobyte of data. Rather, I would be able to reduce the access time. The same thing happens in a program operation where by having separate banks or planes, I am able to program 64 kilobyte of data parallelly. So effectively making these operations parallel, you will be able to improve the performances. So this is a slide about evolution from the floating gate to the replacement gate. From 32 tiers, these are all 3D NAND. From 32 years FG NAND, we went to a replacement RG NAND. RG NAND gives you that flexibility to actually scale. So with FG NAND, the process hit like a roadblock, which means we had to evolve and switch from FG NAND to RG NAND. So today we have, as Venkat already pointed out, on the NAND front, we have the most advanced 176 tiers RG NAND. This is actually, I'm talking about a 1 or 2 year back technology implies we were already at the state of the art or the best in the business at the time. Today, we are doing a lot more number of tiers, which I do not want to reveal in this forum. But yes, we are scaling aggressively and adding lot more number of tiers. What is the primary difference between the floating gate and NAND gate is how you make the cell. If you see these blue rectangles here, that is nothing but the storage node in an FG NAND, and one storage node is sort of isolated from the next storage node. There is a fundamental difference in making the cell itself, and there are other differences which is beyond the scope of this discussion. But in RG NAND, if you see, the storage node is sort of continuous. So yes, it helps them grow taller, but it comes with the challenge as like there is from storage node to storage node interference, which is a big problem. But algorithms have been designed, technology has tried to improve the isolation also in this case. So fundamental by solving these problems and taking the advantage of replacement gate technology, we are able to achieve scaling in the Z direction. So with that, I'll move into the TLC technology itself. So as I said, in an MLC or 2-bit per cell, I was able to create more states by changing the number of electrons. Similarly, in a TLC, like say L0 is a one state, which is not, if I take L0 is nothing but 1, 1, 1. When I go to L1, I start adding electrons. When I go to L2, I start adding even more number of electrons when compared to L1. So by changing the number of electrons, I created like a 3-bit per cell distribution. And now the cell, each cell can contain any one of these different data combinations. So a particular cell can have 0, 1, 1. So we call that in the 0, 1, 1, we call that each one is a logical page. So the first logical page has one data, second logical page has one data in that particular cell, and the third logical page has 0 data. So that is how we say in a TLC, each cell has 3 bits per cell, and each one is a logical page. So you can imagine the amount of data storage. In an SLC, I required 3 pages for first data, second data, and third data. I can just do it using one particular cell in a TLC. So that's how you save area. In a read operation, when I want to read first page, right? First page is nothing but this data. So I will read wherever there is a data change, right? But you will require multiple reads in a TLC as compared to a SLC or MLC, more number of reads in a TLC as compared to an MLC or an SLC to be able to tell them decipher what the first page data is, what the second page data is, what the third page data is, so on and so forth. So the timings or the performance degrades as what I was talking about in the very first slide, but it gives you the area and cost advantage. Read, retry. Now we talked about this, right? As see, this is the time zero. When you just program data, look at there is a gap between L1 to L2, L2 to L3, L3 to L4. Now what happens is, as you program, as you continue to read, right? After you program at time zero, you read that cell continuously for, like, this is similar to what we do in our mobile phones, right? You store a song, you replay that song, however many times you like. Every time you read, what was this beautiful L1 distribution starts to widen up, and it interferes with the L2 or an L0. So the gas. So now, if you look at the intersection between L1 to L2, those cells which are falling in that boundary, the data is unpredictable. So you have error correction mechanisms like read, retry, which implies, so let's say R2 had some read voltage. Okay, you change that to the right, again read, and see if your ECC is able to correct a lot more. Now you the same thing you do, shift the R2 voltage to the left and read again, and you see how, if the ECC, where the ECC is able to do a better job, and use that as the valid data. So this is an effort to minimize the number of errors. Similarly, soft bit. So here what their soft bit read is nothing but for the ECC engine, you try to give more information. So you read at a voltage Rn between two distributions. You pass that information, and also what you do is you read read at levels Rn minus and Rn plus. So anything below Rn minus, it is a solid one, and anything above Rn plus is also categorized as a solid one. This is the other bit of data that you are sending to the ECC engine. But anything falling between Rn minus and Rn plus, you are saying that there is high probability that these bits are unpredictable. So you give that information to the ECC engine so that the efficiency or the ECC can do a lot more effective job in predicting what this data is. Similarly, this is my similarly there is one more ECC helping mechanism called read calibration, where you see, okay, previously I was reading here when the distributions were beautiful. Now the distributions overlapped. So where do I read? How do I figure that out? I start counting and I try to see where these two intersect, right? So here now you will start at the minima where these two are intersecting. So you will place you do an algorithm, you figure out where the intersection of these two levels is, and place your read voltage there. So very pretty fancy read mechanisms are there. So to summarize, right, NAND flash is a data storage memory, which I believe by reducing the cost per gigabit, uh, we probably will be able to replace the hard disk drive market in future, which is like a huge market. As I already said, it's like a series of NAND gates with an NMOS sort of structure. You are able to program data on a 16 kilobyte basis and read back data. Erase is done on a block basis, and the more the number of bits per cell, more the logical pages are there, and there are algorithms and read related operations. When the ECC is not able to correct, you can have these fancy read operations to assist the ECC engine. With that, I will finish my presentation and open up for any questions.
Thanks, Mr. Kalyan. That was really informative session on NAND flash. Yes, I do have a question from audience for you, where they ask for NAND flash. How NMOS body effect impacts performance of stacked NMOS in NAND flash, and how is it mitigated?
So it is. It would be good if the students mention their name, but it is fine. What I would say is, even though it appears similar to a NAND string where transistors are stacked in series, the body is actually a floating body, or it is. It's an independent fourth element that we can control. Yes, body bias has some effect, but very negligible because of the technology or inherent device physics itself.
Okay. Yeah. So as you asked, this question was from Rashmi Sachin.
Thank you, Rashmi.
That was the only one, and I think we had already a couple of questions to Venkat.
Okay.
With that, we'd like to end the presentation, and that's it from track 1 on the tutorial.
Asutosh, sorry for breaking you. I know there is a pretty huge, probably a lot of students in this conference. I would like to wish each and every one of them the best in their careers, and hopefully, we would get to see some of them at least part of Micron in future. But want to wish them the best in their careers, and in these challenging COVID circumstances, would like to request them to stay safe and take care of themselves and their families. And thank you, for VLSID, for giving me this opportunity.